As daylight fades and the turbulence of warm rising air begins to settle, the atmosphere near the ground transforms into something far more stable, almost layered in its stillness. In this quiet shift, the human body becomes newly visible, not to the eye, but to a network of senses that do not rely on sight at all. With each slow breath, a plume of carbon dioxide disperses outward, expanding and thinning, yet never fully disappearing. It drifts through the cooling air in faint ribbons, shaped by subtle currents, rising slightly before spreading horizontally. What seems like emptiness is, in fact, a continuous chemical broadcast, one that carries information about life itself. Within this environment, a mosquito does not wander aimlessly. It navigates with precision, guided by receptors tuned to detect minute changes in carbon dioxide concentration. These receptors, located primarily on its antennae and specialized mouthparts, are sensitive enough to register shifts so small they would be meaningless to most organisms. When a pulse of exhaled air reaches the insect, it does not simply react, it begins to orient. The flight path changes, becoming more deliberate, more aligned with the invisible gradient of gas that leads back to its source. This is not attraction in a simple sense, but interpretation, the reading of a signal written in the chemistry of respiration. As the mosquito moves closer, additional layers of information begin to resolve. Human skin is not chemically neutral. It is a landscape shaped by sweat, microbial activity, and the constant shedding of organic compounds. Bacteria living on the skin break down secretions into volatile molecules, producing a complex odor profile that varies from one individual to another. Some of these compounds, lactic acid, ammonia, and various fatty acid derivatives, are particularly significant. The mosquito's sensory system is equipped to detect them, and more importantly, to integrate them with the carbon dioxide signal already guiding its approach. This integration transforms the encounter from a distant detection into a targeted search. The insect is no longer following a diffuse plume, but narrowing in on a specific host. Heat now becomes a factor. As night air cools, the relative warmth of a human body stands out more sharply. Infrared-sensitive receptors allow the mosquito to perceive this difference, creating a thermal contrast that further refines its trajectory. What was once a broad chemical trail becomes a multi-dimensional map, combining gas concentration, odor composition, humidity, and temperature into a single navigational framework. Humidity itself plays a subtle but critical role. The human body continuously releases moisture through respiration and through the skin. In still evening air, this moisture lingers, forming a localized zone of slightly higher humidity. For a mosquito, this is not merely background information, but part of the signature that confirms the presence of a living host. The insect's sensory apparatus is capable of detecting these gradients, adding yet another layer to the composite signal it follows. Each cue reinforces the others, reducing uncertainty and guiding the insect with increasing accuracy. What emerges from this process is not a random encounter, but a convergence shaped by evolutionary refinement. The mosquito's entire sensory system is built around the detection of vertebrate hosts, and the human body, in turn, unintentionally provides all the necessary signals. In daylight, rising air currents and shifting winds disrupt these signals, breaking apart the chemical plume and making it more difficult to track. At night, however, the environment stabilizes. The plume holds its structure longer, its gradients remain coherent, and the insect's task becomes significantly easier. The encounter, therefore, is not simply about the presence of a mosquito, but about the conditions that allow its sensory world to function with maximum efficiency. As the mosquito closes the final distance, its behavior changes once again. Flight slows, becoming more controlled, almost hovering as it assesses the immediate environment. Visual cues, though less dominant, still contribute at close range, helping the insect avoid obstacles and orient itself for landing. The skin surface presents its own challenges: movement, airflow, and the risk of detection. But the mosquito's approach is calculated. It seeks areas where blood vessels run close to the surface, guided by subtle temperature variations and the texture of the skin. This moment, often perceived as a sudden intrusion, is in reality the culmination of a complex chain of detection and response. The mosquito has not been drawn by a single factor, but by a layered signal that unfolds over distance and time. Each component, carbon dioxide, skin odor, heat, and moisture, plays a role, but none is sufficient on its own. It is their combination, stabilized by the calm of evening air, that makes the human body legible to the insect. In this interaction, there is no intent beyond survival. The mosquito is not seeking to disturb, but to complete a biological requirement, one that supports reproduction and the continuation of its species. Yet for the human, the encounter feels immediate and personal, a reminder that even in stillness, the body is constantly communicating with the surrounding world. The night does not conceal this communication. It amplifies it, allowing organisms like the mosquito to read it with extraordinary clarity. What appears to be a simple bite is, in fact, the end point of a finely tuned sensory process, shaped by evolution, to exploit the quiet chemistry of the night. As evening settles and the brightness of day recedes into a dim, diffuse glow, the human landscape does not fall silent in the way natural environments often do. Instead, it lingers in a state of extended activity, shaped not by sunlight, but by artificial warmth, residual scent, and the slow release of energy stored in surfaces throughout the day. Wooden tables, stone patios, and the outer walls of buildings continue to radiate heat, creating small pockets of thermal stability and cooling air. Within these pockets, the ecological rhythms that might otherwise pause at dusk are subtly prolonged. For a wasp, this is not the end of activity, but a shift into a different kind of opportunity. Unlike many nocturnal insects that rely heavily on darkness-adapted vision, most social wasps are primarily diurnal, their compound eyes optimized for daylight navigation and color recognition. Yet their behavior is not strictly bound to the sun. In environments shaped by human presence, the boundary between day and night becomes less defined. Artificial lights introduce localized zones of visibility, while the absence of wind in the evening preserves scent trails that would otherwise disperse. The result is a fragmented landscape where feeding cues remain accessible, even as the broader environment quiets. A porch light does not replicate the sun, but it creates just enough illumination to extend foraging behavior beyond its natural limits. The attraction is not to humans themselves, but to the byproducts of human activity. Sugary residues left behind on glasses, fruit peels discarded near seating areas, and the faint but persistent aroma of fermented beverages all contribute to a concentrated chemical environment. Wasps possess highly sensitive olfactory receptors, capable of detecting volatile compounds associated with sugars and proteins from considerable distances. These cues are not random, they signal energy-rich resources essential for colony survival. Late in the season, when larvae numbers decline and the demand for protein decreases, adult wasps shift their focus toward carbohydrates. Sugars become fuel, sustaining the workers themselves rather than feeding the next generation. In this phase, the appeal of human food sources intensifies and the overlap between human and wasp activity becomes more pronounced. As a wasp approaches such an area, its flight pattern reflects a balance between exploration and caution. The air, now more stable, allows scent gradients to remain intact, guiding the insect toward specific points of interest. A half-finished drink on a table is not just an object, but a localized hotspot of chemical signals. Ethanol vapors, fruit esters, and simple sugars combine into a detectable plume that stands out against the relatively neutral background of the night. The wasp hovers briefly, assessing the source, then lands with deliberate precision. Its mouthparts are adapted for lapping rather than piercing, suited to gathering liquid sugars from exposed surfaces. In this context, the human presence is incidental, part of the structure rather than the target. Shelter plays an equally important role in this interaction. Buildings, overhangs, and enclosed outdoor spaces provide protection from wind and predators, creating microhabitats that mirror the sheltered conditions of natural nesting sites. A wasp colony established under the eaves of a house benefits from these features, gaining both structural support and a stable microclimate. Even when the main nest is located elsewhere, These areas function as temporary refuges during foraging. As temperatures drop, the ability to conserve heat becomes increasingly significant. Wasps, being ectothermic, rely on environmental warmth to maintain the muscle function required for flight. Surfaces that retain heat, combined with reduced air movement, allow them to remain active for longer periods than would otherwise be possible. This extension of activity carries inherent risks, and the wasp's behavior reflects an awareness of its surroundings. Movements become more measured, with frequent pauses that allow the insect to process both chemical and visual information. Defensive responses are not absent, but they are context-dependent. A wasp feeding on a sugary surface is focused primarily on resource acquisition, yet it remains capable of rapid escalation if it perceives a threat. Vibrations, sudden air currents, or abrupt changes in light can trigger a defensive posture. This is not aggression in the human sense, but a protective reflex shaped by the need to safeguard both the individual and, indirectly, the colony it represents. In the quiet of evening, these encounters often feel unexpected, as though the presence of the wasp contradicts the stillness of the setting. In reality, the stillness is precisely what enables the interaction. Without the disruptive forces of daytime wind and heat, the sensory world of the wasp becomes clearer, more coherent. The signals it relies on, scent, warmth, structural shelter, are not diminished by darkness, but preserved within it. Human environments, with their concentrated resources and modified conditions, effectively extend the ecological window in which these signals remain usable. What emerges is a subtle overlap between two systems operating on different timelines. Human activity, though reduced, continues to shape the environment in ways that remain biologically relevant. The wasp, responding to these cues, does not distinguish between natural and artificial sources, only between signals that indicate opportunity and those that do not. The encounter is therefore not an intrusion, but a convergence, a moment where the extended landscape of human life intersects with the adaptive strategies of an insect evolved to exploit transient resources. In this shared space, the wasp's presence is both a continuation of its daytime role and an adaptation to altered conditions. It is neither fully nocturnal nor strictly bound to daylight, but responsive to the gradients of light, scent, and temperature that define its environment. The quiet of evening does not erase these gradients, it sharpens them, allowing the insect to navigate with a level of precision that might go unnoticed during the more chaotic hours of the day. For the observer, this can feel like an anomaly, but for the wasp, it is simply another expression of a system finely tuned to detect and respond to the smallest changes in its world. In the quiet transition between late evening and full darkness, certain spaces begin to concentrate life in ways that are not immediately visible to the human eye. A garden that seemed ordinary during the day now reorganizes itself around scent rather than color, around temperature rather than sunlight. Pale blossoms that remained inconspicuous in daylight begin to release their fragrance into the cooling air, their chemistry shifting as pollination windows open for night, active visitors. The air becomes layered with subtle signals, each one drifting outward in soft gradients that linger longer in the stillness. Within this environment, a hovering shape enters, not erratic, but controlled, its movement deliberate and finely tuned to the invisible structure of scent and light. This is the domain of the hummingbird hawk moth, an insect whose behavior seems to borrow from both bird and moth, yet is fully its own. The approach of this moth is not guided by chance, nor by any awareness of human presence. Instead, it follows a network of cues that converge in spaces humans have unintentionally designed. Balconies lined with flowering plants, garden beds arranged for aesthetic bloom cycles, and even small clusters of potted nectar sources create concentrated feeding corridors. These corridors do not exist in isolation. They are amplified by artificial light and residual warmth, which together extend the visibility and accessibility of floral resources. For a hovering nectar feeder, this is an efficient landscape, multiple feeding opportunities compressed into a small, stable area, each flower contributing to a composite signal that can be detected from a distance. Unlike many nocturnal moths that rely heavily on scent alone, the hummingbird hawk moth integrates both olfactory and visual information. Its eyes, though adapted to low light, are capable of detecting contrast and movement, allowing it to identify flower shapes even under dim illumination. Artificial lighting, particularly warm-toned sources, enhances this ability by creating localized zones of visibility where petals reflect and edges sharpen. What appears to a human as a softly lit garden becomes, for the moth, a navigable map of potential nectar sources. The insect hovers in place, its wings beating at a frequency high enough to produce a faint, steady hum, stabilizing its position with remarkable precision as it extends its long proboscis into the flower. This hovering behavior is energetically demanding, requiring rapid muscle contractions and a continuous supply of fuel. Nectar, rich in simple sugars, provides the immediate energy necessary to sustain flight. The moth's physiology is adapted to process this energy quickly, converting it into the mechanical work needed to remain airborne. In this sense, each flower is not merely a feeding site, but a refueling station, and the efficiency of moving between them becomes critical. When multiple flowers are clustered together, as they often are in human-managed spaces, the energetic cost of travel decreases, allowing the moth to maximize intake while minimizing expenditure. The presence of a human within this environment does not alter the moth's objective, but it does shape the conditions in subtle ways. Body heat contributes to localized temperature gradients, and even small increases in warmth can influence the evaporation rate of floral scents, intensifying their release. Movement may disturb the air slightly, but in the relative calm of evening, these disturbances are minor compared to the overall stability of the environment. The human becomes part of the backdrop, an element within the system rather than its focus. The encounter, when it occurs, is often brief. A moment where the insect passes close, its path intersecting with the space occupied by the observer, before returning to the flowers that define its purpose. What makes this interaction particularly revealing is the way it highlights convergence rather than attraction. Both species are drawn to the same conditions for entirely different reasons. Humans seek comfort, arranging plants and lighting to create spaces that are visually pleasing and thermally inviting. The moth seeks energy, following gradients of scent and light that indicate the presence of nectar. The overlap is incidental, yet consistent, emerging wherever these conditions align. It is not the human that draws the moth, but the environment shaped around human activity that becomes biologically relevant. In this shared space, the moth's behavior remains focused and efficient, yet it carries an elegance that can feel almost improbable. The precision of its hovering, the controlled extension of its proboscis, and the rapid adjustments of its flight all reflect a system refined through evolutionary pressure. Pollination occurs as a consequence of feeding, with pollen grains adhering to the moth's body and transferring between flowers as it moves. This mutualistic relationship between plant and pollinator is not disrupted by the presence of humans. If anything, it is facilitated by the clustering of resources that human design often creates. As the night deepens, the activity may continue as long as conditions remain favorable. Temperature, in particular, becomes a limiting factor. The moth, like all insects, relies on external warmth to maintain the muscle function required for flight. When the air cools beyond a certain threshold, activity slows, and the feeding corridor begins to dissolve. Flowers close or reduce their scent output. Light sources become less effective as the surrounding darkness deepens, and the gradients that once guided the moth lose their coherence. The encounter, shaped by a precise alignment of environmental factors, fades as those factors shift. What remains is an understanding that such moments are not anomalies, but expressions of a broader ecological pattern. Human spaces, often designed without consideration for nocturnal pollinators, nonetheless recreate the conditions these insects require. The hummingbird hawk moth does not seek out humans, nor does it avoid them. It responds to the structure of the environment, reading cues that are as real and significant as any natural habitat. In doing so, it reveals how easily the boundaries between human and insect worlds can blur, not through conflict, but through the quiet convergence of needs. In the deepening dark, when the last gradients of twilight have dissolved and the sky settles into a uniform field of low contrast, most natural points of reference begin to fade. Horizons soften, silhouettes lose their sharpness, and the visual world simplifies into broad distinctions between lighter sky and darker ground. For many flying insects, this simplicity is not a limitation but a framework, an ancient system of orientation built around the predictable geometry of celestial light. The moon, distant and effectively fixed relative to the Earth, provides a stable reference point. By maintaining a constant angle to this light source, an insect can travel in a straight line, conserving energy and navigating efficiently through the night. It is a system refined over evolutionary time, reliable precisely because its primary reference is so far removed from the variability of the immediate environment. Into this system, human light enters as a disruptive force. A single lamp, a lit window, or the glow from a campsite introduces a new source of brightness that does not behave like the moon. It is close, intense, and highly localized, creating steep gradients of light and shadow that did not exist in the ancestral landscape. For an insect such as the leopard lacewing, whose life cycle spans both larval and adult stages with distinct ecological roles, the adult phase includes flight behaviors that are sensitive to visual cues. While not all individuals are strictly nocturnal, the principles governing orientation in low light still apply, and artificial illumination alters those principles in fundamental ways. As the insect moves through the dark, its sensory system interprets the artificial light using the same rules it would apply to celestial sources. Attempting to maintain a constant angle to a nearby lamp results in a curved flight path rather than a straight one. The closer the insect gets, the tighter this curve becomes, drawing it into a spiral that can end in direct contact with the light source or the surfaces surrounding it. This is not a conscious attraction, but a navigational error, a mismatch between an evolved system and a novel environmental condition. The insect is not seeking the light for its own sake. It is attempting to orient itself within a framework that the light has fundamentally distorted. Around a human dwelling, this effect is magnified by the structure of the environment. Walls, windows, and fabric surfaces reflect and diffuse light, creating a complex field of illumination that extends beyond the original source. A window, for example, acts as both a barrier and a visual extension of the interior space, its glass surface reflecting light outward while also revealing movement and brightness within. To an insect, this can appear as an open pathway, a continuation of the illuminated environment rather than a solid obstacle. The result is repeated contact, brief impacts, followed by renewed attempts to navigate through what appears to be accessible space. The presence of humans within this illuminated zone adds another layer to the interaction, though not in the way it might seem. Skin, clothing, and even breath can reflect or scatter light, creating localized variations in brightness and contrast. A face turned toward a lamp, a hand moving through the air, or the shifting folds of fabric all become part of the visual landscape the insect is attempting to interpret. These elements do not attract the insect in a biological sense, but they alter the distribution of light in ways that influence its flight path. The encounter, when it occurs, is therefore a byproduct of altered navigation rather than targeted behavior. This phenomenon also intersects with the broader ecological dynamics of the night. Artificial lights can concentrate not only harmless or neutral insects, but also predators that exploit these aggregations. Spiders build webs near lamps, taking advantage of the steady influx of disoriented prey. Bats may adjust their foraging routes to include well-lit areas, where insect density is higher than in surrounding darkness. In this way, the introduction of light reshapes not just individual movement patterns, but entire micro-ecosystems, creating zones of increased interaction and energy flow. The lacewing, caught within this system, becomes part of a larger network of relationships that extend beyond its own immediate behavior. Thermoregulation, though less obvious, also plays a role in this altered landscape. Light sources often emit heat, creating small zones of elevated temperature that can influence insect activity. In cooler conditions, these germ microclimates allow insects to maintain the muscle function required for sustained flight. The combination of light and warmth thus reinforces the persistence of activity in areas where it might otherwise decline. The insect remains active longer, navigating a space that is both visually and thermally distinct from the surrounding environment. As the night progresses and conditions change, the intensity of these interactions can fluctuate. Lights may be turned off, reducing the artificial gradients that guide insect movement, or temperatures may drop to levels that limit activity regardless of illumination. Yet during the period when light remains present, the landscape is fundamentally altered. What would otherwise be a diffuse and low-contrast environment becomes structured and uneven, filled with artificial anchors that redirect movement in ways that were never part of the insect's evolutionary history. The encounter between insect and human in this context is therefore not a matter of attraction or intent, but of transformation. By introducing concentrated light into the night, humans reshape the very framework through which insects perceive and navigate their world. The lacewing does not seek out human presence, nor does it recognize the boundaries of human structures. It responds to light, to contrast, and to the cues that have guided its kind for countless generations. In doing so, it reveals how profoundly the night can be altered by even the simplest of human actions, and how those alterations ripple outward through the behaviors of organisms that share the same space. In the quiet margins of evening, where cultivated gardens begin to blend into the darker edges of vegetation, large winged insects settle into stillness. Leaves hold their positions without wind, walls retain the warmth of the day, and sheltered corners, beneath overhangs, along fence lines, within dense foliage, become resting sites, chosen with precision rather than chance. It is within these dim transitional spaces that the owl butterfly withdraws from movement, its broad wings folded vertically, reducing its profile into something that appears less like an animal and more like a fragment of the environment itself. The surface of those wings, patterned with muted browns and soft gradients, interrupts its outline, while the large circular markings, resembling the eyes of a vertebrate predator, remain partially obscured until the angle of light shifts or the wings open. During daylight hours, these butterflies are typically inactive, avoiding the high exposure of open sunlight by remaining within shaded understory layers. As evening approaches, their behavior changes, but not immediately into flight. Instead, there is a period of transition where the insect occupies a threshold between rest and activity, maintaining readiness without drawing attention. This strategy is not simply about concealment, but about energy conservation and risk management. Large-bodied insects require substantial energy to initiate flight, and unnecessary movement increases the likelihood of detection by predators. By remaining still in low-light conditions, the butterfly minimizes both energy expenditure and visibility, relying on its cryptic coloration to maintain invisibility. The human environment intersects with this strategy in subtle but significant ways. Gardens, patios, and building edges often replicate the structural features of natural habitats, providing vertical surfaces, shaded recesses, and vegetation that offers both cover and stability. A wall, slightly textured and uneven in tone, can serve as an effective resting substrate. The residual warmth it emits after sunset creates a microclimate that slows the cooling of the insect's body, maintaining muscle function at a level that allows for rapid response if needed. Thermoregulation in this context is passive but critical. As an ectothermic organism, the butterfly depends on external heat sources to sustain the physiological readiness required for sudden flight. For the human observer, these resting insects are rarely noticed. The visual system, adapted to detect contrast and movement, often overlooks stationary forms that blend into their surroundings. In low light, this limitation becomes more pronounced. Details are lost, edges soften, and the distinction between object and background diminishes. The butterfly, perfectly adapted to exploit this perceptual gap, remains undetected even at close range. It is only when the human enters the immediate space, brushing against vegetation, stepping near a wall, or altering the airflow, that the equilibrium is broken. The response is immediate and forceful. Wings that had remained motionless unfold in a rapid, coordinated movement, generating both visual expansion and aerodynamic lift. The sudden increase in size, combined with the release of stored energy, produces a burst of motion that contrasts sharply with the preceding stillness. In the confined space of a garden corner or near a building wall, This movement can appear abrupt and disorienting, amplified by the limited field of vision available in low light. The butterfly does not hesitate. It launches into flight with a trajectory that prioritizes escape over direction, seeking distance from the source of disturbance. This reaction is not unique to the butterfly, but is part of a broader survival strategy shared among many prey species. What distinguishes the owl butterfly is the scale and visual impact of its response. The large eye-like patterns on its wings, fully revealed during flight, serve as a secondary defense, momentarily startling potential predators. In natural settings, this can be enough to disrupt the attack sequence of a bird or small mammal, creating a brief window in which the butterfly can escape. In human environments, the same mechanism interacts with a different kind of observer, one whose perceptual system is similarly sensitive to sudden movement and unexpected visual stimuli. The human brain, particularly in low light conditions, is tuned to detect motion as a potential indicator of threat. This sensitivity is an evolutionary adaptation, prioritizing rapid response over detailed analysis when visibility is limited. When a large insect suddenly moves within close proximity, the brain reacts before conscious interpretation can occur. The size of the wings, the speed of the movement, and the ambiguity of the shape combine to trigger a heightened response, often disproportionate to the actual risk posed by the insect. The startle is not a reflection of danger, but of uncertainty, a momentary misclassification driven by the constraints of perception. From the butterfly's perspective, this interaction is purely defensive. The disturbance has interrupted a resting phase, and the immediate goal is to re-establish safety by relocating to a new, undisturbed site. Once in flight, the insect seeks areas with similar characteristics: dim light, structural cover, and thermal stability, where it can settle again and resume its low-energy state. The cycle repeats as long as the conditions remain suitable, with each disturbance prompting the same rapid transition from stillness to motion. This overlap between human and insect activity reveals a shared use of space that is rarely acknowledged. The areas humans consider transitional or peripheral, edges of gardens, shaded walls, quiet corners, are often critical habitats for resting insects. The encounter is not initiated by either party, but emerges from this shared occupancy. The butterfly does not seek out humans, nor do humans intentionally seek out the butterfly. Yet their paths intersect because the environmental features that support human comfort also support insect survival. In these moments, the sudden movement that startles the observer is not an intrusion, but a response, a reflex shaped by the constant need to balance concealment with readiness. The owl butterfly, through its stillness and its abrupt flight, demonstrates how finely tuned these responses are, and how easily they can be triggered when the boundaries between species overlap in the dim, shared spaces of the night. As night settles and temperatures begin to fall across the open landscape, the difference between exposed ground and enclosed space becomes increasingly pronounced. Air outside cools rapidly, losing the heat stored during the day, while inside structures, whether a wooden cabin, a fabric tent, or a storage shed, the process slows. Walls absorb and release warmth gradually, surfaces trap moisture, and airflow becomes limited. Within these boundaries, the environment stabilizes into something distinct from the surrounding night: warmer, more humid, and far less variable. It is not designed with insects in mind, yet in its physical properties, it closely resembles the sheltered refuges many species seek for survival. In this contained space, the presence of the Madagascar hissing cockroach is not a matter of intrusion, but of alignment. This insect, native to forest floors where decaying plant matter accumulates and humidity remains consistently high, is adapted to environments that buffer against rapid environmental change. Its physiology reflects this preference. The body is heavily sclerotized, providing protection against desiccation, while the spiracles, small openings along the sides used for respiration, are capable of regulating water loss in conditions where moisture fluctuates. Yet even with these adaptations, stability remains essential. Fluctuating temperatures and low humidity increase metabolic stress, making consistent microclimates highly valuable. Human-made structures unintentionally replicate these conditions with remarkable precision. A closed container, a pile of stored materials, or the interior of a tent can maintain pockets of elevated humidity simply through the presence of organic matter and restricted ventilation. Small food residues, crumbs, plant fibers, or even microscopic traces of organic compounds add another layer, introducing chemical cues that signal potential resources. These cues do not need to be abundant. For an organism adapted to scavenging, even minimal concentrations are sufficient to justify exploration. The environment becomes not just a refuge, but a landscape of opportunity, defined by gradients of scent, moisture, and temperature. Movement within such a space is deliberate and largely hidden. The cockroach does not rely on vision in the way many diurnal insects do. Its compound eyes are functional, but secondary to a more sensitive system of tactile and chemical perception. Antennae extend forward, sweeping the air and surfaces, detecting minute variations in humidity and the presence of organic molecules. Each contact provides information, building a map of the environment that is constantly updated as the insect moves. In darkness, this method of navigation is not a limitation, but an advantage, allowing precise movement through confined and complex spaces without the need for light. The timing of activity is closely linked to the stability of the environment. As external conditions become less favorable, the relative comfort of the enclosed space increases. The cockroach emerges from deeper shelter, crevices, folds of material, or the underside of objects, into more open areas within the structure. This emergence is not driven by the presence of humans, but by the alignment of internal and external conditions. When temperature and humidity fall within an optimal range, metabolic processes become more efficient, and the search for food can proceed with reduced risk of dehydration or thermal stress. Within this microhabitat, interactions extend beyond the individual insect. The presence of multiple organisms can create a layered ecological system, even within a confined space. Microorganisms break down organic matter, producing additional chemical signals that attract scavengers. In turn, the cockroach contributes to this cycle by fragmenting material, increasing the surface area available for microbial activity. This process, though often unnoticed, mirrors the decomposition dynamics of natural ecosystems, where energy is transferred through successive stages of breakdown and consumption. The encounter between human and insect occurs when these overlapping systems intersect in time and space. A hand reaching into storage, the unzipping of a tent, or the movement of an object disrupts the equilibrium. Air currents shift, light enters, and surfaces that were stable become active. The cockroach responds immediately, not with aggression but with rapid retreat. Its legs, adapted for swift movement across uneven terrain, carry it toward the nearest shelter, where it can re-establish contact with the surfaces that define its sense of security. The reaction is instantaneous, a reflex shaped by the constant need to avoid exposure in environments where visibility can mean vulnerability. Despite its reputation, the insect's role within this system is functional rather than invasive. It does not seek out humans, nor does it depend on them directly. Instead, it exploits the conditions that human structures create, conditions that mirror the stable, resource-rich environments of its evolutionary past. The irony lies in the fact that the very features designed to provide comfort and protection for humans, insulation, enclosure, and the retention of heat and moisture, are the same features that make these spaces attractive to organisms adapted to similar constraints. Thermoregulation within this context is passive but effective. By occupying areas where temperature remains relatively constant, the cockroach minimizes the energy required to maintain physiological function. This efficiency allows more resources to be allocated to movement, reproduction, and survival. Over time, such advantages reinforce the association between the species and human-made environments, not through dependence, but through repeated opportunity. As the night progresses and external conditions continue to shift, the enclosed space remains comparatively stable, sustaining activity long after the outside environment has become less hospitable. The cockroach continues its slow, methodical exploration, guided by cues that are imperceptible to human senses. When morning approaches and light begins to re-enter the structure, activity diminishes, and the insect withdraws once more into deeper shelter, where darkness and stability persist. In this cycle, the encounter is neither accidental nor intentional, but inevitable. It arises from the convergence of biological adaptation and environmental design, from the way human structures reshape the immediate landscape into something that aligns with the needs of other organisms. The Madagascar cockroach does not invade, it inhabits, and in doing so, it reveals how closely the boundaries between constructed and natural environments can overlap, especially in the quiet, controlled conditions of the night. As darkness settles fully across the landscape, the structure of movement changes in ways that are not immediately visible but profoundly influential. The open air, once filled with layered currents and shifting thermals, becomes more stable, allowing flight paths to extend farther and with greater consistency. For large-bodied insects, this stability reduces the energetic cost of travel, enabling them to move across broader distances in search of resources, mates, or suitable substrates. Within this quiet airspace, the longhorn beetle takes to the air, its movement defined not by speed alone, but by weight, momentum, and the physical demands of carrying a heavily armored body through still night air. Unlike smaller insects that can hover or adjust direction with minimal effort, longhorn beetles fly with a more forceful rhythm. Their wing beats are slower but powerful, producing an audible vibration that travels ahead of them, a low mechanical hum that reflects the scale of their movement. This sound, often perceived by humans as sudden and intrusive, is simply the acoustic signature of a body adapted for endurance rather than agility. The beetle's flight is purposeful but not highly maneuverable, relying on forward momentum and gradual adjustments rather than rapid changes in direction. In the darkness, where visual cues are limited, this approach is supported by a combination of sensory inputs that guide the insect through its environment. Central to this navigation is the interpretation of contrast. Even in low light, surfaces differ in their ability to reflect ambient illumination. The silhouette of a tree trunk against the sky, the darker mass of dense vegetation, or the faint outline of a structure all provide reference points that help orient movement. Over evolutionary time, these cues have been consistent enough to support reliable navigation. A vertical surface, for example, often indicates a potential host for egg-laying, particularly for species whose larvae develop within wood. The chemical composition of the surface, combined with its texture and temperature, provides further confirmation, allowing the beetle to assess suitability upon contact. Human structures introduce new forms into this system, shapes and surfaces that mimic some of these natural cues while amplifying others. Wooden walls, fences, and beams replicate the vertical orientation and material properties of tree trunks, but they often do so in more uniform and accessible ways. Heat retained within these materials after sunset creates localized zones of warmth that stand out against the cooling environment. For an ectothermic organism, this warmth is not merely incidental, it supports muscle function and prolongs activity, making such surfaces more attractive as temporary resting or exploratory sites. Light, however, is the most significant factor in reshaping this landscape. Artificial illumination creates points of intense brightness that contrast sharply with the surrounding darkness. Unlike the diffuse and distant light of the moon, these sources are close and concentrated, producing steep gradients that can dominate the visual field of a flying insect. As the beetle moves through the night, these illuminated areas become focal points, not because they represent resources, but because they disrupt the normal pattern of contrast the insect relies upon for orientation. Approaching such a light source, the beetle's navigation system attempts to integrate this new information using its existing framework. The result is often a direct trajectory toward the illuminated surface, guided by the apparent clarity of the visual cue. As it nears, the intensity of the light can overwhelm finer distinctions, flattening depth perception and obscuring the true nature of the surface. A wall becomes a plane of brightness, a window a glowing void, and the boundary between open space and solid structure becomes difficult to resolve. The collision, when it occurs, is not the product of attraction in a biological sense, but of misinterpretation. The beetle, moving with considerable momentum, meets the surface with a force that reflects its size and speed. The impact produces a sharp, resonant sound, amplified by the rigidity of both body and structure. For the human observer, this moment can feel dramatic, even startling, as the scale of the insect and the suddenness of the contact combine to create a sense of intrusion. Yet for the beetle, it is simply a consequence of navigating an environment where familiar cues have been altered. Following the impact, the insect often pauses, its legs gripping the surface as it reorients. Antennae, long and highly sensitive, sweep the immediate area, detecting chemical signals that may indicate the presence of suitable substrates. In some cases, the beetle may remain, exploring the surface in search of cues associated with host plants or decaying wood. In others, it may take flight again, departing the illuminated zone and returning to the darker, more predictable structure of the surrounding environment. This interaction does not occur in isolation. Artificial lights can draw multiple insects into the same space, creating temporary tajammuat, where species that would rarely encounter one another converge. Predators may exploit these tajammuat, positioning themselves near light sources to intercept disoriented prey. The beetle, though large, is not exempt from this dynamic. Birds, bats, and other nocturnal hunters may take advantage of the increased visibility and concentration of insects, turning human structures into active feeding grounds. Thermoregulation continues to influence behavior throughout this process. The warmth of illuminated surfaces can extend the period during which the beetle remains active, delaying the cooling that would otherwise reduce muscle efficiency. This extended activity increases the likelihood of repeated interactions with human structures, reinforcing the pattern of encounter. As the night progresses and temperatures decline further, activity gradually diminishes. The beetle seeks out more stable conditions, retreating to areas where it can conserve energy until the next period of favorable conditions arises. The illuminated surfaces that once acted as focal points lose their influence as the broader environment shifts, and the artificial landscape returns temporarily to a state closer to its natural counterpart. The encounter between human and longhorn beetle, then, is not a matter of pursuit or preference, but of convergence shaped by altered cues. By introducing bright, heated surfaces into the darkness, humans create points of interruption in the insect's navigational field. These points, though unintentional, become sites of interaction where the physical realities of insect movement intersect with the constructed environment. The resulting moments, often brief and startling, reveal how even simple changes in light and structure can reshape the pathways of organisms moving through the night. By the time the encounter is noticed, it has already been unfolding for some time in silence. The air inside a room or a tent holds a different quality than the outside night. Less movement, fewer shifting currents, a more uniform temperature that softens the transitions between surfaces. Fabric hangs in gentle folds, walls rise in uninterrupted planes, and seams create narrow corridors where light barely reaches. Within this environment, the shieldbug moves with a deliberate calm, guided not by urgency, but by the steady logic of finding a place to remain undisturbed. The journey into this space rarely begins with intention directed toward human presence. Instead, it is part of a broader movement across vegetation, driven by seasonal change, temperature gradients, or the search for overwintering sites. Many shieldbugs, particularly those inhabiting temperate regions, transition from active feeding on plants to seeking sheltered locations as conditions become less favorable. The shift is gradual, influenced by shortening daylight and cooling air, cues that signal the need to conserve energy and reduce exposure. In natural settings, this often leads them toward bark crevices, leaf litter, or the underside of stones, places where temperature fluctuations are minimized and humidity remains relatively stable. Human structures, however, replicate these conditions with surprising accuracy. A wall, smooth and vertical, provides a stable resting surface that does not shift or sway. Curtains and fabric folds mimic the layered protection of leaves, creating microenvironments where air movement is reduced and concealment is enhanced. The seams of a tent or the interior of a bag offer narrow, enclosed spaces that mirror the crevices found in natural habitats. These features are not designed with insects in mind, yet they align closely with the requirements of species adapted to exploit sheltered environments. As the shieldbug crosses into this space, its behavior remains consistent with its ecological role. It does not rush or explore widely, but instead seeks out a suitable resting point with minimal exposure. The body, shield-shaped and compact, is well suited to this task, allowing it to press close against surfaces and reduce its profile. Its coloration, often a muted blend of greens, browns, or subtle metallic tones, helps it blend into a variety of backgrounds, from plant surfaces to painted walls. In low light, this camouflage becomes even more effective as the human eye struggles to distinguish subtle contrasts and stationary forms. The insect's sensory world is dominated by chemical and tactile information. Antennae extend forward, sampling the air and the surface beneath them, detecting faint traces of plant-derived compounds or the absence of disturbance. Vision plays a secondary role, sufficient for orientation, but not for detailed analysis. This reliance on non-visual cues allows the shield bug to navigate enclosed spaces with confidence, even in near darkness. Each step is measured, each pause a moment of assessment, until a location is found that satisfies the conditions of stability and concealment. Once settled, the insect enters a state of reduced activity. Metabolic processes slow, conserving energy for the extended periods when feeding is not possible. This is particularly important for species that overwinter as adults, relying on stored resources to survive months of limited availability. The choice of resting site is therefore critical. It must provide not only physical protection, but also a microclimate that buffers against extremes of temperature and humidity. Human environments, with their controlled interiors and insulating materials, often fulfill these requirements more effectively than the fluctuating conditions outside. For the human occupant, the presence of the insect remains unnoticed until a moment of proximity brings it into awareness. A hand brushing against a curtain, the shifting of a bag, or the adjustment of bedding can reveal what had been hidden in plain sight. The discovery is often sudden, not because the insect has just arrived, but because it has been still long enough to escape detection. Its response when disturbed is restrained. Unlike more mobile or aggressive species, the shield bug relies on stillness and, if necessary, the release of defensive chemicals to deter potential threats. The odor, produced by specialized glands, is a last resort, a chemical signal that communicates unpalatability rather than initiating conflict. This defensive strategy reflects the insect's position within the broader ecological network. Shield bugs are primarily herbivorous, feeding on plant juices and contributing to the complex dynamics of plant-insect interactions. They are, in turn, prey for a variety of predators, from birds to parasitic wasps, and their survival depends on avoiding detection rather than confronting it. The move into human spaces does not alter this role. It simply shifts the context in which it is expressed. The same behaviors that protect the insect in natural habitats, camouflage, stillness, and chemical defense, operate within the constructed environment. The quiet nature of these encounters can create the impression of sudden appearance, as though the insect has emerged without warning. In reality, it is the culmination of a process that began outside, guided by environmental cues and shaped by the availability of suitable shelter. The human environment, with its stable surfaces and controlled conditions, becomes an extension of the insect's habitat, not through design, but through coincidence. The boundaries between inside and outside blur, defined less by walls and more by the continuity of ecological opportunity. As time passes and conditions change, the shield bug may remain in place for extended periods, emerging only when temperatures rise or when the need to feed returns. Its presence is temporary, tied to the same cycles that govern its life in the wild. When it eventually departs, it leaves behind no trace beyond the brief awareness of its existence, a reminder that the spaces humans occupy are not isolated from the broader ecological systems that surround them. In this way, the encounter is not an intrusion, but a moment of overlap, where the structural features of human environments align with the needs of an organism adapted to seek shelter and stability. The shield bug does not enter with intent to interact, but with the simple objective of finding a place to rest. That this place happens to be within human space is a reflection of how closely constructed environments can mirror the conditions of the natural world, often without being recognized as such. As the temperature begins its steady decline toward the colder margins of the year, the rhythm of insect life shifts in ways that are not immediately visible, but deeply consequential. The open landscape loses its capacity to buffer extremes, and the thin margins that once supported constant activity begin to narrow. Leaves wither, plant chemistry changes, and the abundance of prey species diminishes. For the ladybug, an insect often associated with bright daylight and active predation, this transition signals a profound behavioral change. The same organism that once moved deliberately across plant surfaces in search of aphids now turns its attention toward survival through stillness, seeking a place where the instability of the outside world can be held at a distance. The process begins not with sudden movement toward human structures, but with a gradual aggregation driven by environmental cues. As daylight shortens and temperatures fluctuate more dramatically between day and night, ladybugs respond through a combination of physiological and behavioral adjustments. Fat reserves are accumulated, metabolism begins to slow, and movement becomes more directed toward sheltered locations. In natural settings, these insects often gather in rock crevices beneath bark or within dense vegetation, forming clusters that reduce individual exposure to cold. This aggregation is not random. It is guided by chemical signals, subtle pheromones released by individuals that attract others to the same site, reinforcing the formation of a collective refuge. Human structures, though not part of this evolutionary history, present features that align closely with these requirements. Walls warmed by sunlight during the day retain heat longer into the evening, creating localized zones of thermal stability. Small gaps around windows, door frames, and roofing materials provide entry points into interior spaces where temperature fluctuations are further reduced. Once inside, the environment becomes even more consistent. Air is still, humidity is controlled, and surfaces offer a range of textures that can serve as resting points. To the insect, this is not an artificial environment, but a continuation of the search for suitable overwintering habitat. The transition from exterior to interior often goes unnoticed. Ladybugs are small, their movement slow and deliberate when compared to more active species. They do not rush into space but filter through it, entering through openings that are rarely perceived as significant. A narrow gap along a window frame, a slight separation in siding, or a moment when a door is opened can provide sufficient access. Once inside, the insect seeks vertical surfaces, often moving upward, guided by a behavioral tendency to orient toward higher ground. This movement increases the likelihood of finding stable resting sites, such as ceiling corners, behind curtains, or within the folds of fabric, where disturbance is minimal. As aggregation continues, the presence of multiple individuals becomes more apparent, though still subtle. Clusters may form in sheltered corners, each insect contributing to a microenvironment that further stabilizes temperature and humidity. The combined mass of bodies reduces heat loss, a collective thermoregulatory effect that enhances survival during extended periods of cold. In this state, activity is greatly reduced. The insects enter a form of dormancy, not a complete cessation of function, but a significant slowing of metabolic processes. Energy consumption decreases, allowing stored reserves to sustain them through months when feeding is not possible. For the human observer, the encounter often begins with a single individual, discovered on a wall or near a window, seemingly out of place in an indoor setting. The familiarity of the insect, its rounded shape and distinctive coloration, contrasts with the context in which it is found. Yet this moment is only a fragment of a larger process. The presence of one often indicates the presence of many, hidden within the structural features of the space, occupying niches that mirror the crevices and sheltered surfaces of the natural environment. The timing of activity within this indoor refuge can vary. Warm spells during winter may temporarily reactivate individuals, prompting slow movement across surfaces as metabolic processes respond to the change in temperature. These brief periods of activity can create the impression of ongoing presence, even though the primary state remains one of dormancy. Light, particularly from windows or artificial sources, may draw individuals toward exposed areas where they become more visible before returning to sheltered positions. This interaction between insect and human space reveals a deeper alignment between biological need and environmental structure. The ladybug does not enter the home with awareness of its human occupants, nor does it seek interaction. It interprets the conditions, warmth, stability, and shelter as indicators of a suitable overwintering site. The home, in this sense, functions as an extension of the insect's habitat, offering a level of protection that may exceed that of many natural environments. Within this shared space, the ecological role of the ladybug remains unchanged, even as its behavior shifts. During active seasons, it is a predator, contributing to the control of plant-feeding insects and influencing the balance of agricultural and natural systems. In dormancy, its role is suspended, yet the adaptations that define it, its capacity for aggregation, its sensitivity to environmental cues, and its reliance on stored energy remain evident in the way it occupies the space. The encounter, then, is not an anomaly, but a predictable outcome of overlapping systems. Human structures, designed for comfort and protection, inadvertently recreate the conditions that many insects require for seasonal survival. The ladybug, responding to these conditions, becomes a temporary inhabitant of the indoor environment, its presence a quiet reflection of the continuity between constructed and natural spaces. As the cycle turns and temperatures rise, the process reverses. Dormancy ends, activity resumes, and the insects disperse, leaving the refuge to return to the open landscape where feeding and reproduction can begin again. The brief period of coexistence fades, often leaving little trace beyond the memory of a small, familiar form appearing unexpectedly within the home. Yet within that moment lies a complex interaction, shaped by evolution and environment, revealing how closely the lives of different species can intersect when conditions align. In the dim margins where cultivated space dissolves into unmanaged growth, the boundary between object and organism becomes increasingly uncertain. Branches overlap, leaves cast layered shadows, and the geometry of the environment begins to repeat itself in subtle variations of line and angle. Within this visual complexity, the stick insect does not move through the landscape in the way most animals do. It becomes part of it. Its body is not merely similar to a twig. It is functionally indistinguishable from one under the conditions in which it evolved. The segmentation of its form mirrors the nodes of plant stems. Its coloration shifts across muted greens and browns, and its posture aligns precisely with the orientation of surrounding vegetation. Even its stillness is an adaptation, a behavioral extension of its physical disguise. The success of this camouflage is not absolute, but it is highly effective within the sensory framework of both predator and human observer. Vision, particularly in low light, relies on contrast and movement to identify forms. When neither is present, the brain fills gaps with expectation, categorizing shapes based on familiarity rather than detailed analysis. A vertical line among many vertical lines is assumed to be part of the background. A slight irregularity in shape is dismissed as natural variation. The stick insect exploits this tendency completely, existing within the margins of perception where recognition fails not because the object is hidden, but because it is misinterpreted. As evening deepens, the dynamics of this system become even more pronounced. Light levels drop, reducing the resolution at which the human eye can distinguish fine detail. Colors desaturate, merging into broader tonal ranges, and the distinction between foreground and background weakens. For the insect, this is an advantage. Its camouflage, already effective in daylight, becomes nearly complete in low-light conditions. The absence of wind further enhances this effect. Without the movement of leaves and branches, the entire environment settles into a static composition, and the insect, perfectly aligned within it, disappears entirely. The encounter, when it occurs, is not initiated by the insect, but by the movement of the human observer. A hand reaching into foliage, a foot brushing against low branches, or the simple act of passing through vegetation introduces disturbance into an otherwise stable system. Air currents shift, surfaces move, and the alignment that maintained the insect's invisibility is disrupted. In response, the stick insect may remain motionless, relying on its camouflage to persist despite the change. In some cases, however, it initiates a slow, deliberate movement, repositioning itself to maintain alignment with the altered environment. This movement is not rapid or dramatic, but it is enough to cross the threshold of perception. What was once a static line becomes dynamic, and the brain, suddenly presented with motion where none was expected, recalibrates its interpretation. The twig is no longer a twig. The environment reveals an organism that had been present all along, occupying the same space without detection. The surprise that follows is not a result of the insect's behavior, but of the limitations of human perception, a system optimized for efficiency rather than exhaustive detail. From a biological perspective, this strategy is a direct response to predation pressure. Stick insects are largely defenseless in terms of physical aggression. They do not possess venom, speed, or significant armor. Instead, their survival depends on avoiding detection entirely. Some species enhance this strategy with additional behaviors, swaying gently to mimic the movement of vegetation in the wind, or adopting postures that further break up their outline. Others may drop to the ground and remain motionless, blending into leaf litter if their primary camouflage is compromised. These responses are layered, each one reinforcing the central principle of remaining unseen. The interaction with humans does not alter this strategy, but it reveals its effectiveness in a new context. Human vision, though highly developed, shares many of the same constraints as the visual systems of natural predators. It prioritizes movement, contrast, and recognizable patterns, often at the expense of detecting anomalies that do not fit these criteria. The stick insect, by aligning itself with the dominant patterns of its environment, bypasses these detection mechanisms entirely. The result is an encounter that feels sudden and unexpected, even though it is the product of continuous coexistence. This coexistence extends beyond the moment of discovery. The insect does not pursue or retreat in response to human presence unless directly disturbed. Its objective remains the same: to maintain its position within the environment in a way that minimizes detection. The human, once aware, may adjust behavior, moving more carefully or observing more closely, but the fundamental dynamic does not change. The insect remains where it was, part of the same system, its presence neither altered nor diminished by the act of being seen. In this final convergence, the broader pattern becomes clear. Across different species and contexts, the encounters between humans and insects are rarely driven by direct interaction. Instead, they emerge from overlapping uses of space, from the ways in which both groups respond to the same environmental cues. The mosquito follows chemical plumes, the wasp responds to concentrated resources, the moth navigates corridors of light and scent, and the beetle collides with artificial structures that interrupt its path. The stick insect, by contrast, does not move toward or away from human space. It simply remains, existing within a visual field that humans pass through without fully perceiving. What this reveals is not a world divided between human and insect, but one shared at multiple levels of awareness. Much of this shared space operates below the threshold of conscious perception, defined by signals and structures that are interpreted differently by each organism. The stick insect represents the most refined expression of this principle, demonstrating that the absence of interaction is often not the absence of presence, but the result of perception failing to register what is already there. As the night continues and the environment remains still, the insect resumes its quiet occupation of space, indistinguishable once more from the branches that surround it. The human observer moves on, carrying with them the brief realization that what appears empty is often densely inhabited. In this way, the encounter does not end with the moment of discovery, but extends into a broader understanding that the natural world does not begin where human awareness ends, but continues within it, unseen, structured, and persistently present.